Okay, so in this video we're going to be reviewing the concept of Reynolds Transport Theorem. Okay, so the idea behind Reynolds Transport Theorem is that we need a way to apply conservation laws in fluids, right? And so we have a lot of conservation laws in physics. We have conservation of mass, momentum, energy, etc., right? But typically, the way that these laws are defined, they're defined in terms of systems, and systems being, a fixed amount of mass. But in fluid mechanics, we don't really perform analysis in terms of systems. We perform them on control volumes instead. And there's differences between them. And so we need a different framework on which to perform these or to use these conservation laws on fluids. Okay, and the whole idea behind Reynolds Transport Theorem is that it's kind of a mathematical expression of this kind of very basic idea that as fluid kind of flows into and out of a control volume, it's going to carry physical quantities with them, right? And so just very basically, right? So when fluid goes into a control volume, it's going to carry its mass with it, right? And then when the fluid flows out of the control volume, it's going to carry its mass out of it, right? So we have mass coming in, mass coming out, okay? And so we basically need a way to mathematically quantify inflow, outflow, accumulation, and production of a physical quantity within a control volume, okay? And so an analogy that I like to think of whenever I teach Reynolds Transport Theorem is to think about your bank account, right? And so I know there's my bank account has less money than I would like, but let's think about how the amount of money can change in your bank account. Okay, and by the amount of money I mean accumulation. And so there are three kind of primary ways. And so you can either deposit money, that would be like an inflow. You can withdraw money, which would be an outflow. Or if you have a good bank, a better bank than mine, you can have money that's produced within your account as well, and that's what we call interest. Okay, and we can summarize these relationships with this kind of very basic kind of transaction equation. And so we say our bank account balance is equal to the interest that we gain plus the deposits, right? So those are two things that add to your bank account balance minus the withdrawals. Okay, so let's take the same idea and apply it to control volumes. Okay, and so for control volumes, we have kind of the same idea, where instead of money, we might have some conserved quantity B. And so B might be mass, momentum, energy, we can apply it to anything, right? So the main thing, it has to be conserved. And so what we say instead here is that the accumulation of B within the control volume, right? So maybe like the accumulation of mass is equal to the production of mass within B plus the inflow of B minus the outflow of B. So very basic ideas, just, we're kind of putting it in mathematical form, okay? And so Reynolds Transport Theorem basically takes this basic idea and applies, and quantifies in terms of formulas, right? And so this is kind of the very simple form of Reynolds Transport Theorem we have at the bottom, where we have an accumulation term, a production term, an inflow term, and an outflow term, okay? And so it may look a little bit intimidating mathematically, but let's go kind of term by term and kind of explain what each one means, okay? All right, so let's start with the accumulation term. And so the accumulation term is partial BCD, partial T. And so what this represents is the rate of change of B within the control volume, right? And so that's basically what accumulation is, right? And so the rate of change of whatever you're putting in within that control volume as a function of time, okay? This next term here, may look very similar, but there's kind of a very subtle difference. And so instead of the rate of change of B within the control volume, notice how this is the rate of change of B within the system, okay? And so the system being a fixed amount of mass. And so if within that system B is being produced, or it might be getting destroyed as well, then this term is going to account for that, okay? And so that's kind of the difference between the first term and the second term, one CV, one Cis, okay? Now let's look at the inflow-outflow terms. And so, there's this kind of multiplication of quite a few terms. And so this rho here is the flow density, okay? This A here is the cross-sectional area of the inflow and the outflow. U here I'm using to represent the fluid velocity. And B, little b here, is the property that we're trying to conserve, but it's the intensive version. That means it's big B divided by mass, essentially, okay? And so put all together, that is our Reynolds Transport Theorem, okay? But this equation here is only valid for a simple kind of one inflow, one outflow case. And so for most practical cases, you're going to have multiple inflows, multiple outflows, and your domain might look a lot more different as well. And so the general form of Reynolds Transport Theorem is given by this down below here. Okay, so I know there's a lot of integrals, there's a lot of derivatives, but the idea is still the same. And so we have an accumulation is equal to a production term minus the inflow outflow. Okay, and so because we have an arbitrary surface, the inflow outflow is kind of combined into one, and that last integral there is a surface integral across the entire outer surface of your control volume. Okay. And so, Reynolds transport theorem, mathematically it does look very intimidating, but just kind of remember this, that is basically just a balance between accumulation, production, and inflow, outflow. And if you kind of remember that, I think you're going to be set to go when you start to do control volume analysis, which is what comes after this.